Okay, so in class today we're working on a couple of volumes of solids of revolutions. Okay, and these of course have come from previous calculus tests, right? The first one was from 2012, and the second one was from 2013. Okay, so I believe it looks like number one is calculator okay, and number two is calculator not okay. So let's see how that affects our questions. Okay, number one, R is the region in the first quadrant bounded by the x-axis and natural log and 5 minus x. Find the area of R. Okay, so hopefully you are well acquainted with knowing how to find the area of a region underneath the curve, right? So this is area under the curve. That should tell you that we are taking an integral. Right? An area under the curve is an integral, and an integral is the area underneath the curve. So we have to figure out what our limits of integration are. So the lower one should be the positive 1, and the upper limit should be 1, 2, 3, 4, 5. Right? That is the y, the x-intercept of our other graph. So the area underneath our curve is the top function, natural log x. Okay, so let's think about this again. So if we continue on and go from 1 to 5, right, 1 to 5, and we want the area underneath the curve. Okay, so 1 to 5 is assuming we have the whole entire graph, not just what it shows on the picture. Okay, so I don't know if this is a very good idea to do it completely from 1 to 5. Okay, why don't we break this into 2 and see if we can just use 2 separate intervals with 2 solitary equations. Okay, because it doesn't look like natural log minus 5 minus x is going to do us much good. Okay, I mean, maybe it will, maybe it works, but let's break this into 2. So let's use our calculator, since it's calculator active, and see when the natural log is equal to 5 minus x. Okay, what is that point right there? Okay, so you can use nsolve or regular solve in your calculator. You can graph both of these things and see where they intersect. I don't think solving this by hand is a very good way to go. Right, natural logging both sides, or eing both sides, get rid of that. But then, right, it's not so pretty. So let's use our calculator and figure out where these things intersect. So I get x equals 3.693. That's the intersection point. So we're going to split our interval into 2. So we're going to go from 1 to 3.693. of natural log, and then we're going to go from 3.693 to 5 of 5 minus x dx. Okay, I think that's the best way to do this, right? We're going to find the area underneath both of these curves solo, right, by themselves, and then we'll add them together. I mean, we can go back and check and see if that will work in a second, but let's make sure this one I am 102% sure will work for sure. So let's see. What do we get? So the answer is 2.986. Okay, so when I tried putting the whole thing in there, right, the integral from 1 to 5, a natural log x minus 5 minus x, I got a negative number, so it's not the same thing. Okay, so we're going to split this into 2 integrals whenever we have some type of a crazy intersection here. Okay, part B says rotate it. Let's see, the cross section is a semicircle. Okay, so we're making semicircles, so the it is, what was it? It was pi over 8 is the coefficient. Okay, pi over 8 was the coefficient for the volume solved by semicircles. Okay, so if you remember, probably not, but just in case, right, we had a semicircle, right, where this was the radius, and the radius was half of your function, so natural log x. Okay, that would give you half of, right, if that's the whole entire thing, that's your diameter. So the radius is half of natural log x. So then 1/2 of pi radius squared, okay, was 1/2 of pi times 1/4 of s squared, which is where we get the pi over 8 from. Okay, so when it's semicircles, so we're going to split this into two separate problems, right, just like we had before. We're going to take the natural log semicircles, and we're going to take the linear semicircles. Okay, so we're going to split this into two functions once again. Do the natural log one and then the other one. So natural logs here in red. So pi over 8 times the integral from 1 to 3.693 of natural log x squared, right? So it's pi r squared plus the pi over 8 times the integral from 3.693 to 5 of 5 minus x squared dx. Okay, 5 minus x squared dx. So that's what we're putting into our calculator. Okay, we're splitting this into two separate things rather than keeping it as one complete interval. Okay, because there's a point of intersection. One is not always above the other one. So we're going to use it like this. So let's put that into our calculator and see what we get. So I get 1.093 as that's volume. Okay, so we're not rotating it around anything. We're just drawing a cross section. So we're drawing those pictures, basically building on top of this area. We're building semicircles on top of the area. Okay, so the third part says we have some line y equals k, which is a horizontal line, right? Y equals k is a horizontal line that divides the area into two equal regions. Write but don't solve an equation involving one or more integrals whose solution is the value of k. Okay, so we're trying to divide this into half, right? Half of it. Well, that's pretty okay. Half, right? Half of our area was half of 2.986, right? So that's not hard to do. It's not hard to find half of the area. 0.5 times 2.986. So half of the area is 1.493. Now, how are we going to figure out how this y equation comes into play? Okay, it's pretty okay if we had, well, let's do this. If we were going to find an x equation, and we've done this a little bit before, if we're going to find an x equation, right, a vertical line that divides it into two, let's just say that maybe this is going to be our vertical line. Right, this is k. Then we take the interval from 1 to k is half of the interval from 1 to 5. Right, so that's how we would do it if we were looking for an x line, if x is k. Okay, but since we're looking for a y line, we're going to have to take a y interval, right? So we're looking for a y line that divides this into two. So we're looking for now a vertical, okay, a vertical system. So the interval from 0 to k, right, 0 to k, because now we're looking for, right, it starts at 0. This is definitely 0, the bottom of our graph. And this is, I guess we're going to have to figure out what the y value is. And we can do that simply by subtracting 5 minus 3.693. 5 minus 3.693. This has a y value of 1.307. Okay, so let me erase some of this stuff. This is looking pretty. 1.493. Remember 1.493. So we're going to take the interval from 0 to k on the y-axis of the right function minus the left function. Okay, so this is solved for y. Gee, we've got to do all kinds of stuff here. So we've got to solve it for y. If we have a y interval, we have to solve each of these equations and put them in terms of y. So that means that x equals e to the y, right? That's how we solve this one. We exponentiate both sides. And then x equals 5 minus y. 5 minus y. Okay, so going from right to left, it's the 5 minus y equation minus the e to the y equation. Okay, so we have 5 minus y minus e to the y dy equals the 1.493, which is half of the area. Okay, the area doesn't matter whether it's top to bottom or whether it's bottom to top, right? Or left to right versus right to left. The area of this thing is the same no matter which way we look at it. Okay, so I believe this is, right, it's not pretty and it's definitely not easy to do, but this would be the formula that we would use to find the y value, right, from 0 to k, which is a y interval, because it wants a y equation, that is half of your total area. Okay, so remember when we're doing a y thing, it's right minus left, and thank goodness we don't have to evaluate this. We just have to write it down. Okay, so that was pretty crazy. Deal. Let's see what part B has for us. Question number 5. Here we have your two equations, f and g. So I'm going to assume, because this is a quadratic, right? This is a quadratic equation, that this is your f, right? This is a quadratic equation, so there's your f function. And this one is your trig equation, right? So trig equation is probably this one, which is going to repeat over and over and over. Okay, so g is above f on this interval, I guess from 0 to 2, since that is what we have on your paper. Okay, so the area of R is the integral from 0 to 2 of the top function, g of x, minus the bottom function, f of x. Okay, and this is all you need to put if you're doing an FRQ in calculus. Okay, they know that g of x belongs to this one, and they know that f of x belongs to that. So all you have to do for AP is write down the function names, and that's good enough. Okay, calculator not permitted. I'm going to use my calculator, sorry. I don't want to have to anti-differentiate this thing. And I don't believe you want to either. Even though the 1/4 pi and the 4, it might come out to be nice, but let's not worry about that. Let's just plug it into our calculator. Okay? Remember, on your test tomorrow, you need to be able to anti-differentiate, but there's no trig anti-differentiation on there. It's all polynomials. Okay, so into the calculator this goes. So that's what my calculator says, 3.760. Okay, top function minus bottom function, okay, to find the area between your two curves. Okay, write but do not evaluate an integral that gives the volume generated by the line y equals 4. Okay, so let's draw in the line y equals 4. That looks like a nice horizontal line. Okay, so we want the farther radius, so this is your radius 1, minus the closer radius. Okay, so remember when we're doing this, it's the farther function minus your axis. Okay, so it's always function minus axis squared. Okay, function minus axis squared. So volume is pi times the integral from 0 to 2 of your farther function, which is your f function, right? So f of x minus 4, which is your axis squared, minus your closer function, which is the g this time, minus 4 squared dx. Okay, so that's all they want you to do. And once again, with AP, you don't have to plug in the function. You can use the letter that they give you. So the function notation is good enough for AP calculus. Okay? In fact, it's probably preferred rather than writing out every single thing, especially in this teeny tiny little box. Okay, so that's the front side. Now let me take a picture and look at the back. Okay, so here's the back. We have y equals root x is 0, 0, and 9 rotated about the x-axis. Graph neatly. So let's take some perfect square roots. So 0 is 0. If x is 1, y is 1 because the square root of 1 is 1. When x is 4, y is 2 because the square root of 4 is 2. When x is 9, y is 3 because the square root of 9 is 3. Okay, so this is the region that we are rotating. Okay, so let's just take a second and find the area, right, because we're probably going to need it in a second, from 0 to 9 of root x dx. Okay, so the area of this thing from 0 to 9 root x. So the antiderivative of root x, that's x to the 1/2, right? So we add 1 to the power, which is 3/2, and then divide it by your new power. Okay, so the antiderivative of root x is 2/3 of x to the 3/2. Okay, and now we're going to plug in 9. Okay, we're going to plug in 9. So let's see what we get when we plug in 9. 2/3 of 9 raised to the 3/2 power. Okay, so let's do this systematically. What is 9 raised to the 1/2? So the square root of 9, is 3. 3 cubed is 27, right? 3 cubed is 27. 27 divided by 3 is 9. 2 times 9 is 18. Okay, so then 2/3 of 18, I believe, is 12. Okay, so the area of this thing is 12, right? 2/3 is 12. Okay, all that wonderful, right, simplification of this problem. Okay, so find the value of A on this interval that divides the region into 2 equal parts. So there is some line in here somewhere that we're calling A that makes each of these into 6 square units. Okay, that's what we want. So find it as an exact value and a decimal approximation. So let's see how we do that. Okay, I stand corrected. Thank you. This area should be 18. I 2/3'd it too many times. So our area is actually 18. Okay, so we want to find the area from 0 to something of our root x function that gives me an area of 9, right? I want this to be 2 equal parts. So equal parts of 18 are 9 and 9. So I am looking for some A value where when I take the antiderivative, I get 9. Okay, so of course your calculator can tell you this pretty quick, but let's do it by hand. Okay, once again, the derivative of root x is 2/3 of x to the 3/2 power. Evaluated from 0 to A, that needs to equal 9. Okay, so when I plug in A, I get 2/3 of A to the 3/2 power equals 9. So now it's just a matter of getting A by itself. So first, let's multiply by 3/2. So multiply by 3/2. Okay, so that means we have A to the 3/2 power equals 27 divided by 2, which I believe is 13.5 or something. Okay, and then I'm going to raise it to the 2/3 power. Okay, raise it to the 2/3 power. So I believe this would be adequate, right? This is an exact value. So if you left it like this, 27/2 or 13.5 raised to the 2/3 power, you would get it excellently correct. Okay, but a decimal approximation, right? We can plug this into your calculator and see what it's going to be. So 27 halves raised to the 2/3 power. My calculator says 5.6696, so 5.670 when we round to 3 decimal places. Okay, so I believe that would be about right. Right, would divide these both things into 9. Okay, so part B says something about the volume, right? So volume. So now we are rotating it around the x-axis, and we're going to get a volume. Okay, so volume equals pi times the integral from 0 to a of root x squared dx, right, because it's pi r squared. That needs to equal half of pi times the integral from 0 to 9 of root x squared dx. Okay, so 0 to a needs to be equal to 0 to 9, or half of 0 to 9. Okay, so I think we can pretty much just divide both sides by pi, right? We can divide with both sides by pi, and that's fine. And then, let's see, so we have 0 to a. The root x squared is just x, right? The square root of x squared is just x, equals half of 0 to 9 of x dx. Okay, sorry my a's and my 9's look alike. I agree. I am getting kind of confused. This one is the a. Okay, so this is x squared divided by 2 evaluated from 0 to a, and that equals half of x squared divided by 2 evaluated from 0 to 9. Okay, so on the left side, I get a squared over 2, and on the right, I get half of 9 squared over 2. Okay, so let's see. So multiply both sides by 2. So a squared equals 9 squared divided by 2. So when I take the square root of both sides, I get 9 over root 2. Okay, remember we want an exact value. That is an exact value. It would be okay in calculus if you left it just like that. Or maybe the square root of 81 over 2, right? That would have been also fine because 9 squared is 81. That is good. Now let's plug it into your calculator and get an approximation. 9 divided by root 2. Calculator is 6.364. Okay, so these are not the same points. Dividing the area in half is not the same as dividing the volume in half. Okay, but this is going to be the line that would divide your volume into 2 equal parts. And then 5.67 is the line that divides your area into 2 equal parts. Okay, so remember on your test tomorrow, you have 6 questions that are calculators and 5 questions that are non-calculator. So make sure you're able to take the antiderivative of a polynomial by hand and plug in all the stuff that you need. Okay, remember that there are multiple choice, so there are other options than just using calculus, but your FRQs need to show all of the work. Okay? Hopefully you feel smarter and you'll be great on your test tomorrow. Okay, goodbye.